We can model the cell membrane using the circuit ideas we have learned so far. Let's say we have some potential at a point in the membrane. How will this change as a function of time and space? If we assume no ions of potential escape through our membrane, we can come up with a pretty good model. Using the definitions of current and some nifty algebra, you could show that the potential changes as a function of time according to this equation. Notice that this is really similar to Fick's second law, where we looked at the concavity relative to the concentration over time. So if I look at this graph, I can see that it will smooth out over time, and at the points of inflection, the concentration will stay the same, or in this case, the potential. You should feel comfortable plugging in these dimensions into this equation and understanding how changing those will affect your results. However, in real life, we know that potential and ions can actually cross the membrane, so we don't actually have no leakage. Instead, we can come up with a leaky cable model. In this model, we need to account for some leakage through our membrane, which is described by some resistivity and the same dielectric constant. So why does this matter? Well, if A, the thickness of the membrane, is really small, potential will propagate slowly in our neurons. This is bad because our brains won't be able to tell us what to do quickly enough to respond to stimuli. As a result, we end up with a myelin sheath around our neurons that increases this value A. Therefore, when we increase this value A, we get faster potential propagation. In fact, if you lose that myelin sheath, it's usually indicative of some kind of neurological disorder, like multiple sclerosis or leukodystrophy. The difference between D and A is somewhat subtle, but important. D represents the size of the cell itself. It's the distance between one membrane and the other. A is the thickness of that individual membrane.